Let's look at single sample t-test with variance unknown. Most of the cases, single sample t-test with variance is known is not much useful to us because practically we would not know the population variance. The population mean is a hypothetical value, so there's no question of knowing it. We are testing a null hypothesis about the population mean value. But population variances are things that are not known to us. Say we have data of intelligence quotient, we know the population mean because we believe that intelligence quotient is normally distribution, IQ is normally distributed with a mean 110 and variance standard deviation of 15. In such cases we know the population variances. But in most of the cases population variance is not known to us. And so if we are using this formula z is equal to x bar minus mu upon sigma upon square root n, this sigma would never be known to us. And so we must replace sigma by the sample estimate of sigma, and the sample estimate of sigma is S, or sample standard deviation, divided by square root of n. We know by now that this would follow, this would be a t random variable, right? This would be a t random variable. Now, so when sample variance is not known and we are using S square instead of sample variance, we would use this formula, and this formula would follow a distribution, sampling distribution, which is called as t distribution. Okay. Now, given this, what we are actually trying to do is we are trying to solve a problem. Now, since t is a distribution that is sampling distribution, it will also have degrees of freedom. So this t value will be at df being n minus 1. So the t distribution that we are going to use, say suppose this is a t distribution at n minus 1 at df is equal to n minus 1, then this is the distribution that we would be using to find out the area under the distribution for the t value that we would obtain after this calculation. Okay. Now, we begin with some kind of null and alternative hypothesis. Say, let's assume that we have a null that states that the mean value of neuroticism is 50, and we want to test this null hypothesis. The alternative always is it is not 50. Okay, so mu is 50. The sample that we have obtained has a value 47. The sample standard variance is say 25. So sample standard deviation would be square root of 25, that is 5. Okay, now I compute t, that is x bar, this is the sample mean, 47 minus 50 upon this particular value, that is 5 upon square root of the sample size n that we need to say, n is say 40, right? What's the value that we have taken for n while doing these calculations? 40, yeah, 40. N is 40. So square root of 40. Now this is 3 upon 5 upon square root of 40 is 0.7906, which is equal to 3.794. Okay, this is the value that we have obtained for t. Now, what we need to do is this value of t is under the t distribution at degrees of freedom n minus 1. So this is n is 40 minus 1 is equal to 39. Now what I need to do is I need to find out at 0.05, since generally we set alpha alpha is 0.05, that is the probability of type 1 error is said to be 0.05. We want to know the t-value in this particular distribution, t-distribution, which is at degrees of freedom 39, what is the t-value? Now if we do that, then that t-value is negative, so at t is equal to t at 39 degrees of freedom, if it is equal to plus minus 2.02022, this particular t has a probability smaller than 0.05 or equal to 0.05. Okay, probability is equal to 0.05. So this is if this particular t distribution, if this is t at 39 degrees of freedom, and say this value is 2.022 and this is negative 2.022, this entire area, so if I integrate, what I do is I integrate from negative 2.022 to negative infinity, right, this entire area for fx with reference to x, then, and this f of f is the distribution function of t which we have seen yesterday, then this is equal to 0.025. Similarly, this side would be equal to 0.025. I add up both the areas, so this 0.025 and this side 0.025, I add both of them, it is 0.05, right? So a value of 2.022 has probability, so the chance that you would get a t-value greater than or smaller, greater than 2.022 or smaller than 2.022, this chance is 0.05. So there is a 5% chance in a t distribution at degrees of freedom 29 that you would find a value which has a value smaller than 0.025, 022 is 0.5. That is the chance. Okay, now we have obtained a t-value 3.794, which means that this value is greater than this value, that the value 2.022, 3. Whatever we have obtained, 3.79 and negative 3.79. Probability of obtaining this value or a value greater than this value, probability of obtaining 3.79 or greater than this value has a chance much smaller than 0.05. Probability of obtaining a value of 2.02 or smaller than 2.02, this probability is 0.05. Since t is a continuous random variable, we are interested not in probability of a specific value. We know that any value, any specific value has a probability 0. We are interested in area under the curve, and so we are looking at area from 2.022 till positive infinity, negative 2.022 till negative infinity. Okay, and so we know that chance of obtaining 3.794 is really low. Okay, so what are we saying now? We are saying that if this particular x bar, that is 47, has come from a population that has a mean 50, then the chance of observing this particular value 47 is really low, right? If 47 comes from, if 50 is the mean and 5 is the sample standard deviation with n is equal to 40, then the chance of obtaining 47 as a sample's mean is really low. Now I have two options. I can say that actually 47 comes from a population that has a mean 50. It's one outside observation that I have got. One outside sample I have got. One bad sample that I have got. One very less probable sample that I have got. Or I can say that this sample, since getting a mean of 47 is not much probable, the probability of getting this far a mean from the population mean 50 is really low. I can actually say that this mean 47 comes from some other population mean and definitely is not coming from a population that has a mean 50, right? So if this I can say, then I make a decision of not of rejecting null and perhaps accepting the alternative. And accepting alternative actually is not a great statement because it just says that the population from which this sample is coming does not have a mean